Hello, in this lecture we will find the radius of the small circle. In the drawing we have two circles with an internal lunge between them at this point. Let's call the point of contact between those two circles point N. Okay, at point N they touch each other, and also we know that AB is the diameter of the big circle. That is to say, AB equals 2 times the radius of the big circle, and we also know that AC equals to 9 units and DB equals to 4 units, and also this is a right angle, and this angle is also a right angle, and the small circle has 3 tangents. The first tangent to the circle, to the small circle, is actually this line segment is tangent to the circle at this point. Let's call this point point S. Point S is the point of tangency between the tangent to the circle, and we also have the second point of tangency between the tangent to the circle and the circle at this point. Let's call this point point Z, and we have third tangent to the circle. Line segment CD is tangent to the circle at this point. Let's call this point point M. Again, line segment CD is tangent to the circle at point M. This line segment is tangent to the circle at point S, and the point of tangency between this line segment and the circle is at point Z. Okay. Also, actually this is a right angle, and here we have a straight line. AB is a straight line, so this is also a right angle, and this is right angle, therefore this must be also a right angle, and we want to find out the radius of the small circle. Okay, let's define the center of the small circle as point Q. Point Q is the center of the small circle, and we will define the center of the big circle as point P. Again, point P is the center of the big circle, and okay, so I will write it down. Point Q is the center of the small circle, and the point P is the center of the big circle. Okay, point P is the center of the small circle, and point Q is the center of the small circle, and point P is the center of the big circle. We will define as small r the radius of the small circle. Small r is the radius of the small circle, and we will define capital R as the radius of the big circle. I will repeat again, N is the point of contact between the two circles, and in the next step we will draw three radiuses to the points of tangency between the tangents to the circle. So the first radius, that is to say small r, is the radius of the small circle. This is the first radius. The radius small r is drawn to the point of tangency between the tangent to the circle. Okay, so actually we have a rule, rule number one. Rule number one states that the tangent of a circle is perpendicular to the radius drawn to the point of tangency. So I will read rule number one again. The tangent of a circle is perpendicular to the radius drawn to the point of tangency. So actually here we have tangent to the circle. This line segment is tangent to the circle at point S, and we have radius that is drawn to the point of tangency. That is to say, this radius is drawn to point S, that is the point of tangency. Therefore, according to rule number 1, the tangent is perpendicular to the radius that is drawn to the point of tangency, that is to say, to point S. Therefore, this is a right angle, because of the fact that the tangent of this circle at point S is perpendicular to the radius that is drawn to the point of tangency. This radius is drawn to the point of tangency, that's to say, to point S. Therefore, the tangent is perpendicular to the radius, that is to say, this is a right angle. And we also know that this is a right angle, and in the next step we will draw the second radius to the point of tangency, that is to say, to point Z. Okay, so this radius of the small circle is drawn exactly to the point of tangency, that is to say, to point Z, and at point Z this line segment is tangent to the circle, so the radius is drawn to the point of tangency. Therefore, according to rule number 1, the tangent of a circle is perpendicular to the radius drawn to the point of tangency. This radius is drawn to the point of tangency, that is to say, to point Z. Therefore, the tangent, this tangent to the circle, is perpendicular to the radius that is drawn to the point of tangency. Okay, so this is a right angle, and we also know that this is a right angle. And we will draw the third radius that is drawn to the point of tangency, that is to say, to point M. The radius touches the circle at point M, that is the point of tangency. Therefore, according to rule number 1, a radius that is drawn to the point of tangency is perpendicular to the tangent, or the tangent perpendicular to a radius that is drawn to the point of tangency. Again, this radius is drawn to the point of tangency, that is to say, to point M. Therefore, the tangent is perpendicular to the radius. According to rule number 1, the tangent of a circle is perpendicular to the radius drawn to the point of tangency. This radius is drawn to the point of tangency, that is to say, to point M. Point M is the point that this line segment is tangent to the circle, and so the radius is drawn to the point of tangency. Therefore, this tangent is perpendicular to the radius. Therefore, this is a right angle, and this is also a right angle. Okay, so actually we have in quadrilateral QZMD, we have three right angles, 1, 2, 3. So I write it down. In quadrilateral QZMD, this quadrilateral, it has three right angles. There is three right angles, one, two, and three. We have three right angles in this quadrilateral, and we have rule number 2. According to rule number 2, the sum of the angles in a quadrilateral equals or is equal to 360 degrees. Okay, I read rule number 2 again. According to rule number 2, the sum of the angles in a quadrilateral is equal to 360 degrees. Okay, so actually in quadrilateral QZMD, we know that the sum of the angles is 360 degrees. We have three right angles, so 3 times 90 degrees is 270 degrees. So the fourth angle must complete the sum of the angles to 360 degrees, and we have already 270 degrees, so the fourth angle must be equal to 360 degrees minus 270 degrees in order to complete the sum of its angles to 360 degrees. So 360 degrees minus 270 degrees is the size of the fourth angle. Okay, and 360 degrees minus 270 degrees is 90 degrees. That is to say, the fourth angle is actually a right angle. Okay, this is a right angle. Okay, so actually we have here a quadrilateral with four right angles. Again, quadrilateral 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 QZMD equals as 4 right angles and we have a rule number 3. According to rule number 3, if a quadrilateral quadrilateral has 4 right angles, then it is a rectangle. So I will read rule number 3 again. According to rule number 3, if a quadrilateral has 4 right angles, then it is a rectangle. Okay, so actually quadrilateral QZMD has 4 right angles, therefore quadrilateral QZMD is a rectangle. Okay, I write it down. Quadrilateral QZMD has 4 right angles and therefore according to rule number 3, QZMD is a rectangle. Okay, I will read again the things that I wrote. Quadrilateral QZMD has 4 right angles and therefore, according to rule number 3, quadrilateral QZMD is a rectangle. Okay, so this is a rectangle and we have rule number 4 that states, according to rule number 4, the opposite sides of a rectangle are equal to each other. So I will read rule number 4 again. Rule number 4 states that the opposite sides of a rectangle are equal to each other. So actually QZMD is a rectangle and QZ is the radius of the small circle. And we know that the opposite sides of a rectangle are equal to each other. So actually QZ equals to MD. Okay? According to rule number 4, QZ equals to MD because there are two opposite sides of the rectangle. QZ equals to MD according to rule number 4. QZ equals to MD because there are two opposite sides, but we know that QZ equals to the radius of the small circle. Okay, QZ is the radius of the small circle. Therefore, MD also equals to the radius of the circle. Okay, we can derive this equality that MD equals to R. MD equals to the radius of the small circle. So we can write here that MD equals to R. Okay? So we will repeat on the same process on the quadrilateral SQCM. On quadrilateral SQCM, we have three right angles, 1, 2, 3. And according to rule number 2, the sum of the angles of a quadrilateral is equal to 360 degrees. And he has three angles that are right angles, so they are equal in total to 270 degrees. So the fourth angle must complete the sum of the angles to 360 degrees, so it must be equal to 360 degrees minus 270 degrees. That is to say, the fourth angle is also a right angle. So we have here quadrilateral that has three right angles, and according to rule number 3, if a quadrilateral has three right angles, then it is a rectangle. Okay, so SQCM is a rectangle, and according to rule number 4, the opposite sides of a rectangle are equal to each other. So SQ equals to CM, SQ equals to CM, so SQ equals to R, so CM also must be equal to R. Okay, CM equals to R. It is exactly the same proof as we have done in the quadrilateral QZ MD. We proved that MD equals to R, and exactly in the same way we actually proved that this quadrilateral is a rectangle and the opposite sides of the rectangle are equal to each other, and SQ is the radius of the small circle, so CM, that is the opposite side of the rectangle, must be also equal to the radius of the small circle, because according to rule number 4, the opposite sides of rectangle are equal to each other. So if SQ is R, then CM must be equal also to small r. Okay, so we know that MD equals to R, CM also equals to R, CM equals to small r, MD also equals to small r, and we will define PM as X. Okay, PM equals to X according to our definition. Okay, PM equals to X according to our definition. So the value of CP will be CM minus PM. Okay, I write it down. CP equals to CM minus PM. CP equals to CM minus PM. Okay, again, CP equals to CM minus PM. This line segment, CP equals to CM minus PM, that is X. Okay, so CP equals to CM minus PM, and we have already found out that CM is the radius of the small circle, and we defined PM as X. So actually CP equals to small r minus X. Okay, because we know that CM equals to R and PM equals to X according to our definition. CM equals to small r and PM equals to X according to our definition. So CP equals to small r minus X. CP equals to small r minus X. Okay, so I write it down that CP equals to small r minus X. Okay, in the next step we will calculate the size of the radius of the big circle in two different ways. Actually, AB is the diameter of the big circle. Yes, AB is the diameter of the big circle. That is to say, AB equals to 2 times capital R. Okay, AB, that is the diameter of the big circle, equals 2 times the radius of the big circle, 2 times capital R. So actually AB equals to AP plus PB. Okay, AB equals to AP plus PB. Okay, and actually AP is the radius of the circle, so we'll calculate the value of AP, that is the radius of the big circle. That will be our first equation, and we know that the radius of this big circle is also PB, so we'll calculate the radius of the big circle by calculating the value of PB that actually equals to capital R. Okay, so we'll start to calculate the value of the radius of the big circle, that is AP. We know that AP equals to capital R. AP is the radius of the big circle, so we can we can substitute AP by capital R, because AP equals to capital R, and we will get that capital R that equals to AP actually equals to AC plus CP. Okay, so actually AP, that is the radius of the big circle, equals to AC plus CP. Again, AC plus CP is actually the radius of the big circle, but we know that AC equals to 9 units and CP equals to R minus X. Okay, so I write it down. So actually we will get the value of the size of the radius of the big circle, that is equals to AC, that is 9 units, plus CP, that is R minus X. Okay, so actually we found out the radius of the big circle by calculating it in one side of the circle, but we also can calculate the radius of the circle by calculating it on the other side of the circle. The radius of the big circle also equals to PB. So we will calculate it by the second way. We can write down question number 2 that states that the radius of the circle equals to PB. Okay, PB is the radius of the circle because of the fact that AB is the diameter of the circle, so PB is the radius of the circle and AB also is the radius of the circle. So PB is the radius of the big circle. So we will calculate the value of the radius of the circle by calculating the size of PB. Okay, so the radius of the circle equals to PB, that equals to BD plus MD plus MP. Okay, again AB is the diameter of the circle, so it equals to 2 times the radius of the big circle. AP is the radius of this big circle, and PB is also the radius of the circle. So we'll calculate the value of the size of the big circle by calculating the size of PB that actually equals to the radius of the circle. Okay, so the radius of the big circle equals to PB, and the size of PB is actually PB equals to BD plus MD plus MP. Again, PB equals to BD plus MD plus MP. Okay, so actually the radius of the circle, capital R, equals to BD. BD equals to 4 units, and MD is the radius of the small circle, small r, plus BD plus MP, that is x. Okay, BD equals to 4 units, MD equals to small r, and MP equals to x according to our definition. So we got that the radius of the circle according to equation number 2 is 4 plus r plus x. And we have already calculated the radius of the circle in a different way. So we can, according to equation number 1, the radius of the circle is 9 plus r minus x, and according to equation number 2, the radius of the big circle is 4 plus small r plus x. So we can compare equation number 1 to equation number 2. So we'll create equation number 3 that states that capital R equals to R, and we will substitute capital R in the side of the equation by equation number 1 that gives us the value of capital R, and then we will substitute capital R on the other side of the equation by the value of capital R according to equation number 2. According to equation number 2, that states that capital R equals to 4 plus r plus x. Okay? So we will get that capital R according to equation number 1 is 9 plus small r minus x equals to the r according to the calculation, the value that we get according to equation number 2 is 4 plus r plus x. Okay? Again, we substituted this r by equation number 1, and we substituted this r by equation number 2, and we got that question number 3, that 9 minus r minus x equals to 4 plus small r plus x. Okay, so here we have r in this side of the equation, and we have r in the other side, on the other side of the equation, so we can cancel r. So what is left after we cancelled R is nine minus x equals to 4 plus x. Okay, that is what is left after we cancelled R. 9 minus x equals to 4 plus x. Here we will add we will subtract 4 from this equation and we will get that five minus x equals to x. Here we will add x to this equality and we will get that five equals to 2x. Okay, we got that 5 equals to 2x. We'll divide this equality by 2 in order to get the value of x. X equals to 5 over 2 is 2.5 units. So we got the value of x. X equals to 2.5 units. So after we found out the value of x, we can put the value of x in equation number 1, that is the expression for the radius of the big circle. Expression number 1 states that the radius of the big circle equals to 9 plus small r minus x. Okay, that is equation number 1. But we know that x equals to 2.5 units, so we can substitute x by 2.5 units, and we will get that capital R equals to 9 minus 2.5 units plus small r, or capital R equals to 9 minus 2.5 is 6.5 plus small r. So we know that the radius of the big circle equals to 6.5 plus small r, and the value of x is 2.5 units. Okay, in the next step we will present a new rule, rule number 5, and we will implement rule number 5 in our circle. Okay, so according to rule number 5, if two circles have internal length between them then the distance between their centers is equal to the difference between the lengths of their radiuses. Okay, so I will read rule number 5 again. Rule number 5 states that if two circles have internal lunge between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. Okay, so hopefully we can implement rule number 5 in our two circles, because we have here at point N internal lunge between the two circles. Actually they are touching each other at point N, so they have internal lunge between them, so we can implement rule number 5 that at this situation, if two circles have internal lunge between them, then the distance between their centers, the center of the small circle is point Q, and the center of the big circle is at point P. Therefore, the distance between them is QP. So according to rule number 5, QP equals to the difference between the lengths of their radiuses. Okay, the difference between the lengths of their radiuses is actually capital R minus small r. Okay, so here we have equation number 4 that states that QP equals to capital R minus R. Because capital R minus R is the difference between the lengths of the radiuses, and that is equal to the distance between the two centers, the centers of the circles. That is actually QP. Here we can add R to equation number 4, and we will get that we can add small r. We will get that capital R equals to QP plus small r. Okay, so we have the value of the radius of the big circle, but according to equation number 1, capital R equals to 6.5 plus small r. Okay, we have equation number 1 and equation number 4 that both are the expressions of the radius of the big circle, so we can compare equation number 1 to equation number 4. So the statements of equation number 5 will be capital R equals to capital R. Okay, and then we'll substitute capital R by the value of capital R according to equation number 1, and we'll substitute capital R on the other side of the equation by the value of capital R according to equation number 4. Okay, and we will get that 6.5 plus small r equals to QP plus r. Okay, so we compare the equation number 1 to equation number 4 and we have this expression. Here we have small r on this side of the equation, we have small r on the other side of the equation, so we can cancel r. And what is left after we cancelled r is actually we found out the value of QP. QP equals to 6.5 units. Okay, that is the distance between the centers of the two circles. And we already found out that the value of x is 2.5 units. Okay, so in the next step we will connect together by a straight line points Q and P. Okay, by connecting points Q and P by a straight line, we created a right triangle. The right triangle QPM is a right triangle because of the fact that this angle, angle QMP, is a right angle. Therefore, triangle QMP is a right triangle. So we can use the Pythagorean theorem in order to find out the value of QM, that is the radius of the small circle. According to the Pythagorean theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the square of the hypotenuse is QP square equals to PM square plus QM square. That is according to the Pythagorean theorem. Okay. So, according to the Pythagorean theorem, QP squared, that is the square of the hypotenuse, equals to the sum of the sum of the squares of the perpendiculars, equals to PM square plus QM square. Again, QP square equals to PM square plus QM square. But we have already found out that the value of QP is 6.5, so QP square will be 6.5 square equals to PM square. PM equals to X according to our definition, and we already found out that the value of X is 2.5 units plus QM, that is the radius of the small circle. Okay, so we got this equality that 6.5 square equals to 2.5 square plus r square plus small r square. Here 6.5 square is 42.25 units and 2.5 square is 6.25 units. So I write it down. Okay, so we got that 42.25 equals to 6.25 plus r square. Here we subtract 6.25 from this equality, and we'll get that r square equals to 36. Here we will take a root out of this equality, and we will get the value of the radius of the small circle, that is equals to the root of 36 is 6 units. Okay, so we found out that the radius of the small circle, this small circle, equals to 6 units. Okay, so now I'll summarize the lecture. Actually, we wanted to find out the area of the small circle. We wanted to find out the radius of the small circle. And we have here two circles with an internal lunge between them, and we also have the diameter of the big circle, it is AB. That is to say, AB equals to 2 times the radius of the big circle, and we also have 3 tangents to the small circle. And again, we want to find out the radius of the small circle. Okay, so actually we defined the point Q as the center of the small circle, and point P as the center of the big circle, and we defined small r as the radius of the small circle and capital R as the radius of the big circle. Okay, then we have a rule number 1, that states that the tangent of a circle is perpendicular to the radius drawn to the point of tangency. Okay, actually we have here three radiuses that are drawn to the point of tangency. This radius is drawn to the point of tangency, that is to say to point S. Therefore, this is a right angle because the radius is perpendicular to its tangent, and we also have here this radius that is drawn to the point of tangency. Therefore, according to rule number 1, it equals to 90 degrees, and we have here the third radius that is drawn to the point of tangency, that is to say to point Z, and therefore it is perpendicular to its tangent. This is the tangent to the circle. This is actually the tangent is tangent to the circle at point Z, and the radius is drawn to the point of tangency, that is to say to point Z. Therefore, according to rule number 1, this angle is a right angle because the radius is perpendicular to its tangent. Okay, so we have here a quadrilateral QZMD is a quadrilateral shape with three right angles, 1, 2, and 3. Those are right angles, and we note that the sum of the angles in a quadrilateral is equals to 360 degrees according to rule number 2. Okay, so the fourth angle must complete the sum of the angles to 360 degrees, so the value of the fourth angle must be equal to 360 degrees minus the sum of the other three angles, that is to say 360 degrees minus 270 degrees equals to 90 degrees. That is to say this is also a right angle. So we have here a quadrilateral that has four right angles, and according to rule number 3, if a quadrilateral has four right angles, then it is a rectangle. So quadrilateral QZMD, this quadrilateral, is a rectangle according to rule number 3. Okay, so we know that the opposite sides of a rectangle are equal to each other according to rule number 4. Opposite sides of the rectangle are equal to each other. Therefore, QZ equals to MD because those sides are opposite to each other. And we know that QZ equals to small r, so MD that equals to QZ must be also equals to the small r. Okay, we know that QZ equals to MD according to rule number 4, that opposite sides of a rectangle are equal to each other, but we know that QZ is the radius of the circle, it equals to r, so we can derive from this equality that MD also equals to r. Okay, then we repeated on the same process in quadrilateral SQCM, this quadrilateral, we know that three angles of this quadrilateral are equal to 270 degrees, so the fourth angle must be equal to 90 degrees in order to complete the sum of the angles to 360 degrees, because the sum of the three angles is 270 degrees, and in order to complete the sum of the four angles to 360 degrees, the fourth angle must be equal to 90 degrees. So we have here quadrilateral with four right angles. So according to rule number 3, this quadrilateral is a rectangle, and according to rule number 4, opposite sides of the quadrilateral of a rectangle are equal to each other, so SQ equals to R, and we know that SQ equals to CM according to rule number 4. Therefore, CM must be equal also to R, to small r. Okay? So, CM equals to small r, and MD equals to small r. Then we defined line segment PM as X, and actually CP equals to R minus PM, or CP equals to CM minus PM. Okay, CP equals to CM minus PM. Okay, CP equals to CM minus PM, but we know that PM equals to X, and CM is the radius of the small circle, so CP equals to small r minus X. Okay, then we calculated the radius of the big circle in two ways. Actually, AB is the diameter of the big circle, so it equals to 2 times the radius of the big circle, and AB equals to R plus R, that is 2R. AB equals to AP plus PB, that is actually R plus R, so AP equals to capital R. So that is our equation number 1, that states that AP equals to capital R. And what is the value of AP? AP equals to AC plus CP, and AC equals to 9 units, and CP equals to R minus X. So actually capital R equals to AC, that is 9 units, plus CP, that is R minus X. That is equation number 1, that is the expression of the radius of the big circle from one side of the circle, and then we created the expression of the radius of the big circle from the other side of the circle. The radius of the big circle also equals to PB. Okay, we calculated the radius of the big circle on the other side of the equation, that is equals to PB, and PB actually equals to BD plus MD plus MP. PB equals to BD plus MD plus MP, but we know that BD equals to 4 units, MD is the radius of the small circle, and the PM equals to X according to our definition. So actually the radius of the big circle, when we calculated it on the other side of the circle, equals to 4 plus R plus X. So we calculated the values of the big circle in 2 different ways, and of course they are equal to each other. So we have equation number 3 that states that R, the radius of the circle as we calculated it in one way, equals to the radius of the same circle as we calculated it on the other way. R equals to R, and we got the equation number 3 that from equation number 3 we got the value of x equals to 2.5 units. So according to equation number 1, r equals to 9 plus small r minus x, and we know that x equals to 2.5 units. So the radius of the big circle according to equation number 1 is 9 minus 2.5 plus r, or the radius of the big circle according to equation number 1 equals to 6.5 plus small r. Okay, and then we presented rule number 5, and we implemented rule number 5 in our drawings. According to rule number 5, if two circles have internal length between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. Okay, so the distance between the centers of the two circles that have internal length between them is actually the difference between their radiuses. Okay, so we implemented rule number 5 in our circle because we have internal length between those two circles at point N. They are touching each other at point N. Therefore, we can implement rule number 5 that states that the distance between their centers, that is to say QP, equals to the difference between the lengths of their radiuses. That is to say QP equals to capital R minus small r. Okay, that is equation number 4 that states that the distance between the centers of the circles, that is to say QP, equals to the difference between the lengths of their radiuses, that is to say equals to capital R minus small r. But we have equation number 4 that states that so from this equality we got that capital R equals to QP plus small r, and we have equation number 1 that states that capital R equals to 6.5 plus r. So this is the two expressions, two different expressions of the same radius of the big circle. So of course they are equal to each other. So equation number 4 equals to equation number 1. Okay, capital R equals to capital R. Here we substituted capital R by equation number 1, and on the other side we substituted capital R by equation number 4, and we found out that QP equals to 6.5 units and X equals to 2.5 units. Okay, so we connected together points Q and P by a straight line. So the green triangle is a right triangle because of the fact that this is a right angle, angle Q and P is a right angle. We proved that it's a right angle. Therefore, triangle Q and P is a right triangle. So we can implement the Pythagorean theorem in order to find out the value of QM, that is the radius of the small circle. Because we know that QP equals to 6.5 units, and PM that equals to X equals to 2.5 units. And the only missing variable is the radius of the small circle. So we can implement the Pythagorean theorem in order to find out the radius of the small circle. According to the Pythagorean theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, QP squared, that is the square of the hypotenuse, equals to the sum of the squares of the perpendiculars, equals to PM squared plus QM squared. And again, we know that QP equals to 6.5 units, and PM, that is X, equals to 2.5 units. And the only missing variable here is small r. So we put the data inside this equality, and we found out that the radius of the small circle equals to 6 units. Again, the radius of the small circle equals to 6 units. Okay, thank you very much.